Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
We've all typed an address or a domain name into a web browser and loaded a web page. But we know that computers use IP addresses to communicate, so how does a web address turn into an IP address? This is achieved using the domain name system, or DNS. Much like your phone, which can find a phone number to match a contact, a DNS server can find an IP address to match a name. The internet without DNS is truly unimaginable, so let's take some time to appreciate how this indispensable service works. Before we look at how DNS works, we need to understand the domain name space. Here we have a typical name chosen completely at random. As you can see here, there are several parts to this name which are separated by dots. Here we have www, network direction, and net. Even though we don't always see it, there's always a dot at the end too. Often web browsers and other applications hide it, so we don't often think about it. This full name is called the Fully Qualified Domain Name, or FQDN. Now this may not be obvious to look at, but a name like this one is part of a hierarchy. It's a bit like creating a family tree. We read a name like this from right to left, starting with the dot. The dot is the root domain and represents the start of the family tree. Under that comes the top level domains, or TLDs. In our case, this is net, but there are other types like com and org and others. Sometimes there's even a country included, like co.uk or net.au. Under the TLD comes the second level domain. For us, this is network direction, but this could be almost any name. In some cases, we would find more subdomains under that. In our case though, we have a host name, www. For our example, this host name is used to represent our web server. Now we can think about how a DNS server fits into the picture. The DNS server contains one or more special databases called zones. The zones represent the domains, such as networkdirection.net. Each zone contains pieces of information called records. There are different types of records, which we'll look at soon, but the most common one is the host record, also known as the A record. And this contains the name to IP mapping for all the hosts within this domain. Windows Server is probably the easiest way to get started with DNS, so we're going to have a look there. Over on the left, we have forward lookup zones and reverse lookup zones. For now, we're interested in forward lookup zones. And here we have a zone that I created earlier. I would like to take this opportunity to encourage you to build a small lab and try creating your own zone. And don't worry, it's not very hard to do. Inside our zone, we have a few records. The top two, the start of authority and the name server records, are special records which are used to describe the details of the zone and the DNS server. The next two are both A records, which hold a name and its IP address. In both cases, they're pointing to my server. There's not a lot to them really, they're really quite simple. If a DNS server has a zone for a particular domain name, then this server is authoritative for that domain. So this server here is authoritative for networkdirection.net. This means that the server believes that it knows all there is to know about this domain. So if someone tries to look up mail.networkdirection.net, this server will simply say, no, this record does not exist. Why is this important? Well, because if this DNS server is non-authoritative for a domain, it's willing to admit that it doesn't have all the answers, and it may ask another server for help. And we'll see that happening in a few minutes' time. If you want to see some of this in action, you can run the nslookup command from a Windows command prompt. Linux has a similar command called dig. We can try two lookups. Notice that one is non-authoritative. This means our DNS server doesn't own that domain. There are a few more record types that you'll probably come across. We'll take a quick look at three of them now. Over here we've got the reverse lookup zone, and with that belongs the pointer record. This is the reverse of what we've discussed so far, as this is used when you know an IP address but you don't know the name. And the zone itself looks a bit different. As this relates to IP addresses, each zone is named after a subnet. Also, the FQDN is in reverse, which I guess is appropriate for a reverse lookup zone. And it's always followed by the text in ADDR ARPA. This is a fixed string of text that indicates that this is a pointer record. Okay, so the next one of interest is called a CNAME or canonical name record. This, really simply, is just an alias. For example, we already have an A record called www, but we might also want a new record called web, and it should point to the same IP. So one of our options is to create a CNAME record which maps web to www. And this is really good if the IP address changes. That means we only need to update one of our records, not all of them. And the last one we'll look at quickly is called a mail exchanger or MX record. This is how we advertise the IP addresses of our mail servers out to the internet. So say a mail server somewhere out on the internet wants to send us some mail, it will look up this record, it will learn the IPs of our mail servers, and it will know where to send the mail to. Now we'll take a moment to look at a simple DNS lookup process. Here we have a DNS server and a client. The client is configured with the IP address of the DNS server. This can be done manually, as we're showing here, or the client can be given the IP of the DNS server through DHCP. When the client needs to perform a name lookup, it sends a message to the DNS server using UDP port 53 as the destination. This message includes the fully qualified domain name that it's looking for. When the message arrives at the server will check if it is authoritative for this domain. In this example, it is. So it will look for the requested record inside the zone. If the record is there, it will then return the IP address to the client. On the other hand, if the server does not have the requested record, it will send a message to the client saying that it does not exist. And as this server is authoritative for the requested domain, it can indeed say this with confidence. When the client gets this result, whatever it may be, it will store it in the local cache. It does this for performance, so it won't need to ask the server again for some time. But how long is it stored in the cache? That's based on a value called the TTL, or time to live. If we enable advanced view here, and then we open a record, we can see the record's TTL. And this is set to 1 hour. So this record would stick in the client's cache for 1 hour, and then it would be removed. Once it's gone from the cache, if the client needs the record again, it will need to perform another lookup. If we open a command prompt on Windows, we can look at the cache. First, we'll ping an address by name to perform a DNS lookup. And now if we type in ipconfig/display DNS, we can see the record in the cache. New records get added every time there's a lookup. What happens though if a change is made to the A record on the server? Our client won't know about the change until the record has been cleared from the cache. So for troubleshooting, you'll occasionally want to clear out the cache manually. On Windows, you can do this with ipconfig/flushdns. I've got a few quick troubleshooting tips for you now. If DNS is not working, start by checking the DNS settings on the client. You can do this in Windows with the ipconfig/all command. If there's no problems there, try pinging the DNS server to see if it's even responding. If the server's down, it certainly can't help. Then try clearing the cache, which we went through just a few moments ago. And if none of this is working, you can always try bypassing the DNS server entirely and setting manual records. On Windows, we have something called the hosts file, which contains manual entries. You can Google that yourself if you'd like to have a look. And on a Cisco router, we use the IP host command to enter manual entries. Keep in mind though that bypassing a DNS server should really only be done for testing. You don't want to leave those records in there permanently, as it can confuse your results in future. Now let's get to a more complicated example. Think about when we need to look up a name on the internet. Let's imagine that our client wants to browse to this URL. First, it will need to perform a DNS lookup to resolve blog.cloudflare.com to an IP address. So just like before, it sends a message to the DNS server. However, our DNS server is non-authoritative for the cloudflare.com domain. So how does it handle this query? Our server simply can't answer this query on its own. So now it becomes the client and sends a query to another DNS server. If the outside DNS server knows the answer to this query, it will send the answer back to our server. Our DNS server will cache the result to save time if it's asked again, and will send the result to the original client. The server's cache follows the same rules, and the cached record will be removed when the TTL expires. This process, where the DNS server finds the answer on behalf of the original client, is called a recursive query. Here's an interesting thought though. How does our server know where to send this query? Surely there's thousands of DNS servers out there on the internet. One option is to configure the DNS server with a forwarder. This is one or more IP addresses that our server can send requests to. The other option, if no forwarders are configured, is to use root hints. Remember from earlier that the dot at the end of the FQDN is the root of the namespace? Well, there are 13 IP addresses for special DNS servers around the world, which are called root servers. These are authoritative for the root namespace, which means that they know how to find the name servers for top-level domains like .com, .net, .org, and so on. So going back to our example, the client sends a request to the DNS server, which the DNS server doesn't know how to answer. The server has no forwarders configured, so it relies on the root hints process. DNS servers come pre-configured with the 13 IP addresses for the root servers, so our server will pick one, and it will send it a query asking where blog.cloudflare.com is. Now the root server doesn't have all the answers either, but it does know how to find the DNS servers that are responsible for all .com domains. So the root server will send back a message called a referral containing the IPs for these servers. This type of request is called an iterative query. This is different to a recursive query, as our server is just getting hints back. The root server doesn't take over the process, our server still has to work it out on its own. And so the process repeats. Our server sends a request to one of the .com DNS servers that I just learned about. This server also doesn't have the full answer, but it does know which DNS server to use for cloudflare.com, and so it will send a hint for that back. Our server continues the process and sends a request to the Cloudflare DNS server, and finally we've found the server that is authoritative, and it returns the answer that we're looking for. And just as before, the record is put in the DNS server's cache, and a response is finally sent back to the original client. Now I've got a few interesting questions for you this time around.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.